Okay, so today what we're going to be doing is we're going to derive the slope and the intercept coefficients for ordinary least squares using the methods of moments approach. So suppose you're interested in estimating a linear relationship between our output yi and our input variable xi. And there's also some error term here which represents the difference between our predicted value of y and the actual observed value of yi. So we have two unknowns here, beta naught and beta 1, and what we're going to do is we're going to find out the OLS values of those coefficients. So we need a few key assumptions here to get us on our way. So first assumption here is equation number 2, which states that the expected value of u given any value of x is going to be constant. So over here in this graph, you can see that to be the case. So when x is equal to 90, you see this distribution. Now this normal distribution, let's say that's the distribution of u. That's still the same than as when we jump over here to say x is equal to 115. The distribution of u is still the same. So given any value of x, we expect for our mean of u to not change. Furthermore, we're going to state that the expected value of u is going to be 0. And one of our last assumptions is that the covariance between our independent variable and the error term is 0. So you can see this here in this graph. As x increases, the distribution of our error term does not change at all. So there's no relationship between u and x, as evidenced in this graph. So now what we're going to do is we're going to go back to equation 1, and we're going to take this, solve it for ui, and then we're going to plug that into equations 3 and 4. So where there was the expected value of u equals 0 previously, now we've just inserted this nice long term here. Same goes for equation 6, where there was the product of x times u. Now we've just substituted in for u. But the thing is, those equations are the population equations, and what we need is the sample counterparts. So the sample counterpart of the expected value operator is the mean. So what we're going to do here is we're going to take those equations and we're going to divide by n, and then we're going to sum up over each term. So all n terms we're going to sum up over those terms, and we're going to do that for both equation 5 and equation 6. So what we had before was the expected value operator. Now we're just taking the mean of each ith term here. So we need a few more properties here to go through the derivation. The first property is from Appendix A, A.2, which states that if we're summing up over a constant, we can actually pull out this constant and sum up over 1, and then the result of that is c times n, because if we sum up 1 n times, we end up with n. Property 8.3, we're summing up a constant c times an index variable xi, and what we can actually do is we can pull out the term c, and then we can sum up over all of the xi's. Property 8.4 tells us that our summation operator is actually a linear operator, and we can apply it to each term. So say here, if we expand out that expression and we write out each single term all the way until the nth term, we can then break this apart and we can rewrite this in terms of the x's, and then we can also rewrite this in terms of the y's. Furthermore, we can factor out the common terms here, a and b, for those terms respectively, and we can recast this as actually a times the summation of all the x's plus b times the summation of all the y's. So you can think of almost like distributing the summation operator if it's multiplied by a series of terms that are added inside of parentheses. So now we can solve for beta naught hat. So applying the expected value operator to equation 1 and using the properties just discussed, we end up with an equation that looks like this. So essentially what we're doing is we're taking the mean of both sides of the equation. And on the right hand side I color coded the terms. The first term is red, then orange, then blue. And I just did that just to help us see how the math traces out as we go through this derivation. So in the next step, what I did is I just applied the mean operator to y to get the mean of y. On the right hand side, what I did is I distributed the summation operator, and I also distributed this n to the negative 1 power, dividing each term by n. Next, what I did was I pulled out the constant. So beta naught hat, the slope, and the intercept beta 1 hat are constants. And so you can actually pull those out of the summation operator. Next, I did a little bit of math. We know that if we sum up 1 n times, we end up with n. So we move on to the next term. If we're summing up all of the x's and then we're dividing by n, what we're actually doing is we're taking the sample mean, so that's the mean of x, and then this last term, this blue term, we know that we've defined the sample mean of u to be equal to 0, so we're just applying that property there. So we end up with these equations. The mean of y is equal to beta naught hat plus beta 1 hat times the mean of x, and beta naught hat is equal to the mean of y times beta 1 hat times the mean of x. So here we have one unknown, which is beta 1 hat. So what we're going to do is then we're going to go back to equation 8, and we're going to plug in for beta naught hat. So we end up with an expression that looks like this. Next step, what I did was I just distributed the xi terms. Then I regrouped this so that on the right hand side here, I took out the common factors, which was beta 1 hat and xi. Then I distributed the summation operator in such a way that it broke up the equation into two chunks. And then last, what I did is I actually subtracted this term from both sides of the equation. And what it ends up doing really is it flips around these terms in the parentheses. Before, when we had x bar minus xi, now we have xi minus x bar, which is what happens when you multiply anything by a negative 1. So now, solving for beta 1 hat, I divide both sides by the summation of xi times xi minus the mean of x. And we can make more sense of this expression if we apply property 8.8. So 8.8 tells us that all of these expressions are equal, are the same. So what I'm going to be concentrating on here are these underlined parts right here, because that's the same as the second expression in property 8.8. I'm going to go ahead and I'm going to use a different color. And what we're going to do here is we're going to replace what's underlined in red with what's underlined in orange. And I'll explain this property in a later video so you can understand how 8.8 is true. So when we make that substitution, we see that we still have a little bit more work to do. We can simplify the denominator here because we have the same expression times itself, which is the definition of a squared term. And you can conceptually think of beta 1 hat as taking the sample covariance of x and y divided by the sample variance of x. So there's a lot to think about there conceptually. So essentially what this is saying is, if there's any sort of linear relationship between x and y, that'll be picked up by the numerator, and that relationship is going to be scaled. It's going to be divided by the variance of x.